Okay, so that's that done. We'll put that on the side. So I just thought before we get started for today, does anybody have questions about the strike business that I will try to answer? I don't know all the answers, but I won't tell you any lies.
So the labs are happening as usual, right?
Labs are going ahead. That website, I don't know, that kind of auto-populated about paused versus continuing. It says on the website that one of our lab sections is paused and two are continuing. That is untrue. I confirmed with the head of the department this morning, all of our lab sections are going ahead. So if you're unsure about any of your other courses, I would encourage you to reach out to your instructors and ask, just to check. Yeah.
Is there any chance our labs are gonna go online, or like, are we gonna cross picket lines to go to the lab?
Well, there's a doozy. As far as I'm aware, there is no intent for physics labs to go online, which would result in, if you're coming to the lab, to cross the picket line. Now the question you didn't ask is, what if you feel uncomfortable crossing a picket line? And I understand some people may be in that situation. So I would urge you, if you're uncomfortable crossing a picket line, and that's gonna be your reason for not coming to a lab or something, if there's a strike, then I guess I won't say contact me, because I won't really be allowed to communicate on that issue. But please get in touch with your lab instructors. Neither I cannot speak for the faculty as a whole, I'm just one person, but neither I nor the lab staff wishes to make you do something that you're uncomfortable with. Okay, I thought that was gonna go a lot longer. Yep.
This isn't really about this class in particular. It's just like if they strike, what do you think the likelihood is of them extending the semester or losing a week?
What do I think? So this is just me personally. I think if there's a strike for about a week, I think there'll be no change. I think if it goes on longer than a week, I think we'd see days added to the end of the semester. I don't really think they're gonna cancel break week. I wouldn't see that happening. So it's just kind of from my experience with the university. Another alternative to, and they've done this in the past, rather than extend the semester, they could start making up some stuff on Saturdays. That's happened in the past. But I wouldn't be surprised, if we're longer than a week, I wouldn't be surprised to see Saturdays and semester extended. That would get into exam period. People may or may not have trips planned, flights paid for and booked. In those cases, like if you were my student and you had a flight because you were going wherever for the summer, I would work with you about the final exam to deal with that. Yeah, that would be my intent, and on that issue I can't speak for other professors. But I don't want anybody canceling their summer plans for a physics exam. I wouldn't do it if I was a student. Okay, good enough. So let's get going on today. So the things we covered last day was to talk about a capacitor. We defined capacitance. We introduced the idea of a dielectric as a piece of insulator that we stick between capacitor plates. We started to do an analysis of what happens when we put that dielectric in there, and that's where we'll keep going today. So what we did our last slide of last class was we wrote down our symbols for charge, potential, charge density, and capacitance. We wrote those symbols down for if there was nothing between the plates. That was our subscript of 0 to indicate just empty space, air, or vacuum. Then we put the dielectric in and we had new symbols. We said we saw experimentally that the potential difference between the plates here would drop when we insert the dielectric if we disconnect the battery first. So we outlined all of those things. And we worked it through to show that our capacitance would increase. So then we started to think about why did that happen. So this is our 2D picture. If we have a positive plate and a negative plate, those two plates have a separation of charge. They will create an electric field that we called E0. When we put the dielectric in between the plates, what's going to happen with those dielectric materials, the molecules inside, they're gonna feel an electric force because F is Q times E, and the molecules are gonna tend to align at least a little bit with that electric field that's established by the plates. So these are pictures of my molecules showing that the positive end kind of pushes this way and the negative end pushes this way. That leads to a slight separation of charge inside the dielectric. Separation of charge leads to a new electric field inside the dielectric. And we called that electric field E with an I on it for the induced electric field inside. So that's how far we got last time. So now we look at our capacitor with the dielectric. There are two fields here, so to get the net field, we would just add them up. So that'll be our next step. So the net field between those capacitor plates is E. It's the vector sum of the field without the dielectric plus the field inside the dielectric. So it's the vector sum. If we look at our signs here, then our net field E will point to the left, same direction as that field EO. The EI, the internal one, lines up in the opposite direction, so that gets a minus sign. So that's the magnitude of the field between the plates. The original field, and it's lessened by what's happening within the dielectric. So this shows us that the total electric field is going to be less than that original electric field without the dielectric, because we're subtracting something. Okay, so we're good here? So that's our total electric field between those two plates. So we know that the electric field is different when we put the dielectric in. How different it is, we describe that using what's called a dielectric constant. Okay, so the change in electric field is described by that. So we define the dielectric constant that has a symbol of the Greek letter kappa. It's kind of a fancier K. And that is defined as the field without the dielectric divided by the field with the dielectric. Okay, so it's just the ratio of those two fields. This dielectric constant is more or less a measure of how well molecules can polarize inside that dielectric, how it's going to respond to that field. Some of them will polarize really well, some of them not so well. Okay, so there's a difference in materials. Our dielectric constant kappa is always bigger than 1, and it has no units. So where else can we pull this dielectric constant in? So where can we see that that's useful? So if we take this expression, we see that E is equal to E0 divided by the dielectric constant K. So just solved for E there. E0, my original electric field, would be the charge density divided by epsilon naught. So if I pull that in, it looks like this. And this epsilon naught times kappa, that's how we find the permittivity in a material. So epsilon naught is how electric fields move through a vacuum. Epsilon is how electric fields move through a material. Okay, still good? So this is the one we're probably going to use the most often. This is where you'll see kappa pop up more than anywhere else. Most of our equations will give in terms of epsilon naught. You know, if we have a dielectric, instead of epsilon naught, we're going to use kappa times epsilon naught. So that's where you're going to see it most of the time. In terms of our potential, let's see now if we can explain that drop in potential. So the potential difference between the capacitor plates when there's a dielectric, or delta VC, is the electric field between the plates times the plate separation D. This electric field is our original field divided by kappa, that's times D. EO times D, that's the original potential, EO times kappa. So delta VC, the potential between the plates with the dielectric, is equal to the original potential divided by a constant which is bigger than 1. This explains why the potential drops. Okay, so it drops because of that presence of the dielectric. Okay, and then we'll also look at what happens to the capacitance. So our capacitance in the capacitor with the dielectric, that's C, that's equal to the original charge divided by the potential between the plates of the capacitor, delta VC, so this is with the dielectric, equals QO divided by delta VO over kappa. Okay, so I'll just put in my expression for delta VC here in my denominator. My kappa is in the denominator of the denominator, so kappa times QO over delta VO. That's my original capacitance, CO. So my new capacitance is the dielectric constant times the original capacitance. So this shows that the capacitance increases when we put a dielectric in, which is the whole point. We want to make the capacitance bigger so that it can store more energy. Okay, any questions? Yeah.
Shouldn't it be minus E into D for voltage difference?
Oh, here?
Yeah.
Oh, I suppose if I wanted to get really careful, I'd put the magnitude of the potential difference is the magnitude of the electric field times D, because we're just talking about the size here, okay? So not so much interested in which plate is high and low potential. That's taken care of with everything. So this means the magnitude of the potential. Yeah, good catch.
And kappa can only be determined experimentally, right?
As far as I know, that's true, but I haven't read much about the theory of it. Yeah. And it's definitely material dependent. Depends on whatever kind of material we're using. Okay, and I guess it would be easy enough to measure, right? You just have a capacitor with and without the dielectric. You measure the potential, and it's easy to find the dielectric constant. Okay, so how about I give you a hint? So all of the work we just did, our starting premise was we started with our capacitor, we detached the battery, and then we put the dielectric in. How would it be different if we reverse the order? So what if we had our capacitor, we put in the dielectric, and then we took the battery off? So that would be a good sort of thing to try and work through to see if you could see what would be different and what would be the same in those situations. Okay, so let's go back to an example we did last class where we had a capacitor and we figured out the area of the plates. Let's do that again, but let's have a dielectric between the plates this time. So here's our capacitor. We know the capacitance. We know the plate separation. This time we have a dielectric between the plates, and the dielectric constant is 300. Remember, there's no units here. So we know that capacitance is epsilon times A over D, which is kappa times epsilon naught times A over D. Trying to find the area. So the area is the capacitance times D divided by kappa times epsilon naught. 1 farad times 1 millimeter divided by kappa, which is 300, times epsilon naught 8.85 times 10 to the minus 12 farads per meter. That would give us an area this time of 3.77 times 10 to the 5 meters squared. Last time we got an area, I asked you to think, was that a reasonable area or not? I'll ask the same question, is this a sensible area? If you said it was a square, it would be about 614 meters by 614 meters. So do we like the size of that capacitor? I'm thinking not so much. That's way too big, right? We're not gonna fit that anywhere. So again, that's backing up the idea that 1 farad is huge, and we don't really have capacitors of 1 farad here. That would be something really special. Mostly microfarads, nanofarads, stuff like that. Okay, questions? All right, let's get started on another example. So for this one, 2 10-centimeter diameter electrodes. Right off the bat, you need to read that first phrase. If it talks about a diameter, these are capacitors that have circles for their plates. Okay, so the area is going to be pi r squared for this one. 0.5 centimeters apart, so that's D. They make a parallel plate capacitor attached by metal wires to the terminals of a battery, so that's the potential difference. What's the charge, the electric field, and the potential difference between the electrodes when we do different things to the capacitor? So let's just start by drawing what we have. So here's one plate, here's the other plate, separated by a distance D. That distance D is 0.5 centimeters, or 5 millimeters, or 5 times 10 to the minus 3 meters. The diameter is 10 centimeters, 0.1 meters. Put that here. We're going to connect it to a battery, so let's make a little circuit diagram. That's the positive potential, so this plate will be the positive plate. And this will be the negative plate. And we get our electric field generated in between those two plates. Okay, so that's the first part. We've got our picture drawn. Then part A says, oh yes, and that battery had potential 15 volts. I'll squeeze that in my picture too. So part A is all about what's happening while the battery is connected to the capacitor. So we haven't disconnected anything, we haven't done anything. What's the charge, what's the electric field strength, and what's the potential difference? Okay. I think the easiest question to answer first for part A is what's the potential difference between the electrodes? Okay. It's hooked up to the battery, all the charges are at equilibrium, this thing is fully charged. When that happens, the potential difference across the capacitor plates is the same as the potential difference across the battery, equals 15 volts. Okay, because it's still hooked up, so it's got all charged up. The electric field strength, so that means the magnitude of the electric field. That's the potential difference divided by the plate separation. That gives us 3,000 volts per meter. And what's the charge on each electrode? A couple of different ways to do this. If we remember that the electric field is the charge density divided by epsilon naught, we could then remember that the charge density is Q over area. So then our charge, Q, would be the electric field times the area times epsilon naught. So that lets us use all the information we have right there. The area means the area of the circular plate, pi r squared. Epsilon naught. Put our numbers in, 3,000 volts per meter times pi. The diameter is 10 centimeters, the radius is 5 centimeters. Times epsilon naught, 8.85 times 10 to the minus 12. That gives us a net charge of 2.08 times 10 to the minus 10 coulombs. The question doesn't ask, but I think maybe it could have asked and possibly should have asked, what's the capacitance of this capacitor, since that's the section we're doing. So why don't we put that in as a little bonus? What is the capacitance? So two ways to find capacitance. You can do A times epsilon naught over D, or you can just do charge over delta V. They'll give you exactly the same answer, 13.9 times 10 to the minus 12 farads. questions? So that's our part A. Part B, so we use insulating handles. Okay, so we use something wooden or plastic. We pull the electrodes away from each other until we double the plate separation, but we leave it connected to the battery the whole time. So we've got a new situation here. Let's just sketch out a new picture, part B. So this time, one plate is here, one plate is here. Our new plate separation D is equal to 1 centimeter. We're still connected to the battery. So we still have a plus plate and a minus plate. So now let's go through the process again, see what changes and what's the same. It's still connected to the battery, so the potential difference doesn't change. 15 volts. Our electric field, that depends on the plate separation, delta V over D, so that one's going to change. We get a new electric field of 1500 volts per meter. And then to find our charge, we can use the same expression we had up here. Q is equal to E times pi times R squared times epsilon naught. If we put our numbers in, we get our new charge to be 1.04 times 10 to the minus 10 coulombs. Okay, so when we doubled the distance between the plates, we had the electric field. When we did that, we also had the charge. So what that tells us is that we pulled the plates apart with the battery attached, and it changed the charge on the plates, right? The charge started to flow a bit, right? Because the electric field changed. Okay, part D, our bonus. Oh wait. 1, 2, 3. Our capacitance, A epsilon naught over D, or Q over delta V. If the charge gets cut in half, the capacitance is also going to get cut in half, 6.95 times 10 to the minus 12 farads. Okay, so that's what happens if we pull them apart and we keep the battery connected. And I don't know exactly how they manage this one. Somehow they stretch the electrodes until they're 20 centimeters in diameter, and they still stay connected to the battery. So they increase the area while it's still connected. I don't know if they get a big rolling pin or something, they just flatten it out like pizza dough. Anyway, I took the question out of your book, but it is interesting to see the effect of changing the plates. Maybe it would make more sense if we hooked it up to a capacitor with the same battery, just with bigger plates, get a new one. But anyway, they've rolled them out, so we'll roll them out. So for part C, now we've got new plates that are bigger. We're going back to the original distance, D, 0.5 centimeters. Our diameter now is 20 centimeters. And let's see what happens. So we're still connected to the battery. That means that potential didn't change. Delta V equals 15 volts. Our electric field is the potential divided by the plate separation. The electric field doesn't change. Okay, so no difference there in the electric field because that only depends on potential and separation. Our charge, Q, is the electric field times pi times R squared times epsilon naught. The net amount of charge we can store is bigger because we have a bigger radius. So our net charge stored on the plates is 8.34 times 10 to the minus 10 coulombs. So there's bigger, we've got more room to store charge. And our capacitance, Q over delta V, or A times epsilon naught over D. If we make A bigger, we're going to make our capacitance bigger. That turns out to be 55.6 times 10 to the minus 12 farads. Okay, questions? Okay, that takes us right up to the end of time, so we'll quit there, and, maybe I'll see you Monday, maybe I won't. So you know where to find me if you have any questions.
Will they send out an email, like, on Monday morning or Sunday night or?
So all I've seen is that the
Or I
uni-
guess you'll see on the news.
definitely on the news, it'll be all over the news, you'll see it. But all I've seen is that the university intends to communicate with you through the MunSafe app. That's all I've seen them say. But when in doubt, if you send me a message just asking, hey, is there a strike or what, I'm allowed to answer that one.
Okay.